Information, in the context of our everyday lives, seems like an abstract concept that lies outside our abilities to quantifiably measure it in any meaningful way. How much information do we gain from observing a particular event? Well, intimately connected with information is the idea of our uncertainty surrounding an event. Given a model of a phenomenon, how unexpected is this event to occur or be observed? This is the main concern of information theory, developing measures related to the relative uncertainty of an event so as to provide some form of quantification of information. Since we are interested in examining uncertainty or unexpectedness, we naturally turn to probability theory because probability models help to signify a mathematical methodology for drawing inferences about the world of information. Thus, for an event that occurs with probability p, information theory strives to establish a usable measure or quantity of the information we gain from observing this event. Note that we're only concerned with its occurrence, so each event can be effectively represented as a symbol contained within a set. This way, we can define the information solely in terms of the probability of occurrence. To develop our information measure I of p, we must stipulate its necessary properties that represent the fundamental axioms of this theory. First, information is a non-negative quantity, so I of p is greater than or equal to 0. Second, if an event occurs with probability 1, we obtain no information from its occurrence because we already know it will happen, so I of 1 is 0. The third axiom signifies the critical property of summation of information. It states, if two independent events occur, then the total information we receive from observing this scenario is the sum of the two individual information measures. Lastly, the information measure is continuous and monotonic in the probability p, such that slight changes in probability generate corresponding slight changes in information. From these axioms, we can easily derive the following. For p between 0 and 1, and a being a real positive number, we have I of p to the a is equal to a times I of p. For those individuals with a mathematical background, this important relation should look very familiar for a particular type of function, logarithms. Thus, our information measure can be defined as the following logarithmic function, where the minus sign comes from the fact that a more probable event will provide us with less information than an event that occurs less often. The base b of the logarithm is simply a positive quantity that determines the units we are using. In our case, we typically consider base 2, which has the units of bits. Now that we have defined our information measure, we can now apply it to a simple system. In this case, a source is providing a stream of symbols out of n possible symbols, emitting them independently and with probabilities p1, p2, up to pn respectively. Our interest concerning the system is determining the average amount of information we receive from each symbol observed. Thus, our desired quantity is a weighted average over the number of observations. For instance, if we track the received symbols for a considerable amount of observations, say n, we know that a particular symbol ai will approximately appear n times pi times. Then, given that the information provided by each observation of ai is log of 1 over pi, we can see that in n independent observations, the total information gained will be the sum over all the possible symbols of the number of occurrences multiplied by the information gained from each observation. Therefore, the average information obtained per symbol observed is simply the total information divided by the number of observations n. This key quantity, derived in Shannon's work in 1948, is entropy, h of p. As a more formal statement, given a particular set or distribution of probabilities p, the entropy of the distribution is given by this expression, where in the case of a continuous probability distribution, the summation becomes an integral. Considering the applications of this theory, the entropy function h can be utilized to provide another line of reasoning that supports the second law of thermodynamics. For instance, we can contain n gas particles in a box that is subdivided into 10 to the 6 smaller cubes and examine the possible configurations of the particles in a fashion similar to that of macrostates. In determining the number of possible configurations for both the low and high entropy states, the relative probability that a system starting in a low entropy configuration will transition to a higher entropy configuration turns out to be essentially 1. Therefore, it is overwhelmingly probable that as time passes, the macroscopic system will increase in entropy until it reaches its maximum, which is equivalent to what is stated in the second law of thermodynamics. Finally, a topic of interest that highlights the potential of applying information theory to various scientific fields is the analysis of genomes. For this biological application, we will examine E. coli strain K12 substrain MG1655 version M52, which has been completely sequenced and contains over 4 million nucleotides. The main idea of this exploration is, Given our knowledge of DNA as a coding system, we may be able to find relatively important stretches of DNA that will have a different entropy from other stretches. Since coding sequences for peptides and proteins are encoded in the DNA via codons, which are sequences of blocks of triples of nucleotides, we can consider each set of 3 nucleotides to be a distinct symbol of our source. Therefore, our basic model is to take a chunk of the E. coli genome and estimate the probability of occurrence of each codon by simply counting and dividing by the length of the chunk. More specifically, a window is slid over the entire genome sequence, and an estimate of the entropy within the window is obtained for each step. In doing so, we obtain this plot of the entropy estimates for the actual DNA strain. As you can see, there are distinct locations in our data measurements where the entropy is noticeably lower than its surrounding estimates, with some slightly smaller periodic dips in between. This seems to suggest that there is something significant about these particular stretches of the genome. The first question one might ask is, are these lower entropy measurements directly tied to specific codons within the genome? To answer that question, we can generate a semi-random strain of DNA that has the same ratios of particular codons as documented in the actual strain. In doing so, we can compare the entropy estimates for the two strains on the same plot, as shown here. Given that we do not observe any similarities in the structure of the two signals, we can conjecture that the entropy estimates are in some way linked to the actual location of the codons within the genome. Thus, this begs the question, are these locations of lower entropy at all connected with the location of essential genes that code various proteins and/or amino acids? While this is still a topic undergoing research, initial evaluations suggest that the lower entropy peaks could possibly correspond to large stretches of non-essential codons within the genome. Further analysis still needs to be done, but these initial results demonstrate an exciting possibility to develop an algorithm that helps locate essential stretches of DNA strains amongst the non-essential nucleotides without resorting to brute force examinations. Overall, these two examples prove the multitude of doors that information theory can open when we apply its ideas of information and entropy estimates to different forms of data. Thanks to the landmark work of Claude Shannon in the mid-20th century, we are able to draw quantifiable inferences about our knowledge of the world around us. Lastly, I would like to thank the work of Tom Carter on Introduction to Information Theory and Entropy. His discussion of the material and insights to important ideas helped guide this introductory video on information theory. Thank you.